Okay, guys, here it is, the bedtime story of muscle contraction. And I've got one of your Sarcomere models here created by a student in my class, and I'm going to use it as I tell the story, okay? So here we go. Once upon a time, you wanted to contract a skeletal muscle. And so your brain sent a very small electrical current known as an action potential down the axon of a neuron to the synaptic terminal. When that little electrical current arrived at the bottom of the neuron on the axon, it opens up a voltage-gated channel for calcium, and calcium comes into the end of the axon terminal. That calcium triggers the end of the axon to release the neurotransmitter acetylcholine that was stored in vesicles. The acetylcholine is able to diffuse across the synaptic cleft, and then it binds to ligand-gated sodium channels for which it is the ligand. So when the acetylcholine binds to the channel opens, and sodium, which has been pumped into the synaptic cleft by the sodium-potassium pump, rushes into the muscle cell and causes a change in the electrical potential inside the muscle cell and generates a new current. Now, to get rid of the acetylcholine, we have an enzyme in the synaptic cleft called acetylcholinesterase, and it breaks down the acetylcholine, which closes the sodium channels. Meanwhile, that small electrical current or action potential that we made in the muscle cell travels along the sarcolemma, and everywhere the sarcolemma goes down into the cell in the form of a T-tubule, the action potential will go down, and it will interact with voltage-gated calcium channels on the sarcoplasmic reticulum. This will cause those calcium channels to open, since there's a change in voltage, and all of the calcium that's been stored inside the sarcoplasmic reticulum will come flooding out by diffusion and find its way down to our sarcomere. So here's our sarcomere. And remember, this is a Z disc or Z band. This is a Z line or Z disc or Z band. Here is my M line. And where the calcium goes is it comes over to the thin filament. And on this model, the thin filament is represented by red with green and yellow. The green is my troponin, and troponin is the bouncer. So it changes shape to bind the calcium. And since it is also bound to the yellow rope here, the tropomyosin, when it moves the tropomyosin and uncovers the binding sites on the actin for these myosin heads that are represented here in blue. So the calcium is released, the troponin binds the calcium moves the tropomyosin, and now these myosin heads, which have already taken an ATP molecule and broken it down and are waiting, just vibrating with energy, are going to grab their binding spots on the thin filament, and then they're going to form a cross bridge. They're going to flex at the hinge in a power stroke, and then if there's another ATP nearby, they will let go and do it again. So we will start to see the myosin heads pulling the actins in towards the middle of the sarcomere. And when we have run out of room in the H zone and in the I band, but the A band is the same length, now we have increased the zone of overlap to its maximum length, and the muscle is fully contracted. This sarcomere part is fully contracted. In order to relax that muscle, we have to remove the calcium, which is an active transport process. We have to pump it back into the sarcoplasmic reticulum. That costs us ATP. Then the troponin will relax and put the tropomyosin back over the binding sites. Meanwhile, we had to have the ATP available for the myosin head to let go of the actin to bind the new ATP. And then once it's covered up, then this will slide back apart and the sarcomere is relaxed. The end.